Activity 2. How do waves propagate? Objective: to understand the way waves and sound propagate and their properties as well. This activity was made by Ángel Adrián Nogales Dávila, Seani González Ortiz, Carlos Solórzano.
A wave refers to the oscillation present in nature. Mechanical waves, acoustic waves, water waves, electromagnetic waves, seismic waves, and many more with which natural phenomena can be studied. A wave is made of four parts: the crest, that is the maximum positive displacement from an equilibrium position; the trough, that is the maximum negative displacement from an equilibrium position; the amplitude, that refers to the distance from an equilibrium position to the crest; and the wavelength, that is the length from crest to crest or trough to trough in one cycle. We can calculate many parts of the waves, like the speed, the linear density, the frequency, the wavelength, the period, the spread speed, the intensity, the frequency, the amplitude, and many others. When a wave is on a tensioned cord and both ends are attached, if you form a wave, it will travel from one end to the other and go back inverted. When both waves meet, you get a node. And when both waves are perpendicularly away, it is called an antinode. When waves that are at different frequencies meet, they create a single vibration with a higher amplitude and resonant frequency. The lowest resonant frequency is a natural frequency and has one antinode. If there's more than one antinode, the resonant frequency will increase. Resonant frequencies are called harmonics too, and each harmonic corresponds to their number of notes. The first harmonic has one note, the second harmonic has two notes, the third harmonic has three notes, and it goes on like that. There are many different ways in which sound can be transmitted. For example, sound can propagate through fluids because of the ways that travel that makes the molecules vibrate, and thus propagating the sound in fluids are in that type pack, so it's not as hard as a solid but not as loose as a gas. Also, sound can propagate through gases. The molecules are distributed far from each other, which makes it easier for sound to travel through it. Also, in a metallic rod, for example, it can be the sound that the leg of a metallic table produces when you hit it. Molecules are tightly packed in solids, and this is why the sound extends through their surface more than in other mediums. In an extended solid, the case is pretty similar to the previous one, but the materials vary. So we might not use metals only, but other materials. There are some cases in which properties such as the wavelength and the frequency vary depending on the tube of sound it's being propagated, is closed or open. In table number 3, we can observe a table with the properties of the waves, their description, and an image, so it is easier to identify them. In the superior left side, we can see the crest, that is the highest amount of positive displacement from the equilibrium. On the contrary, in the inferior left side also, we can see the trough, that is the highest amount of negative displacement from equilibrium. The amplitude is located in the middle, on the left side, that is the distance from the equilibrium to the crest. And the wavelength is in the middle also, but refers to the whole length from crest to crest.
Point 4. Mechanical waves. Mechanical waves are the ones that require a medium to travel. For example, sound waves that require air, or sea waves that require water. There are two types of mechanical waves: longitudinal waves and transverse waves. Longitudinal waves are the ones that follow the particles follow the movement of the wave, and transverse waves are the ones that go perpendicular to the movement of the wave. And that's the main difference between both of them. Point 5 and 6. We made a chart that describes the differences between longitudinal waves and transverse waves. As we mentioned before, the difference is that transverse waves go perpendicular to the movement of the wave, and in longitudinal waves, the particles go in the same motion and direction of the wave. And as you can see, we have the formulas that are used to calculate the velocity and the frequency of both waves. Also, we gave them an example that is the UV waves, the radio waves, sound waves, and many more.
I'm in love with the shape of when we let the story begin. We're going out on our first date.
For anthem 1, we use the frequency as 1.5 Hz, the amplitude as 0.5 meters, and 4 notes. With these three data, we have to obtain the velocity and the wavelength. First, we obtain the wavelength with the equation 2L over n, that is equal to 2 plus 0.075 meters over 4, which are the notes, giving us as a result 0.0375 meters, and with that information we can obtain the velocity, which the equation is wavelength multiplied by the frequency, which is 0.0375 by 1.5 Hz, and it gives us as a result 0.05625 meters over second.
I'm in love with your body.
In the anthem number 2, we change the amplitude to 0.8 meters, giving us as a result the wavelength 0.0375 meters, and as a velocity multiplicating 0.0375 meters per the hertz, which are 1.5 hertz. It gives us as a result 0.05625 meters per second.
I'm in love with your body. Last night you were in my room.
In the last attempt, we changed the frequency to 1.8 Hz and the amplitude we changed it to 0.5 again. This giving us as a result 5 notes. So we have to do again the equation of wavelength, which is 2L over n. So is 2 multiplicating by 0.075 meters over 5, which gives us a result of 0.03 meters, and that result we have to multiply it by the frequency. In this case is 1.8 Hz, giving us a result of 0.054 meters over second. And with this we complete the table.